the efficiency right there. It's about 250 grams of fuel consumed per kilowatt hour produced by the engine. Down here, you're consuming twice as much fuel to get the same amount of power. This is what's called the sweet spot of an engine. Right here is where you get the most net power per unit of fuel consumed. Ideally, an engine would never operate outside of this point. That would give you the best fuel economy versus the amount of power output of the vehicle.
What's your x-axis?
Excuse me?
What was your horizontal axis? What was?
Okay, I'm sorry. This is engine speed. You go from 1,000 RPMs to 6,000 RPM, and this is engine torque.
So the idea is you run your engine always on the sweet spot.
That would be ideal.
So you are going to use electric motor, hybrid electric vehicle.
What's that?
Hybrid electric vehicle. So you are talking about hybrid electric vehicle.
Yes.
You want to run your engine always on the sweet
Right.
spot.
Right, but the type of transmission that I believe the Ford Escape and the Toyota Prius has been considered a CVT transmission based on the fact that they can get a change in gear ratio by controlling the electric motor, and I'm going to get to that. The standard OEM technology today is use an automatic transmission. That's what's generally most popular in America. And what they do is they use a set of planetary gears, and a planetary gear consists of a ring gear, which is this large gear right there, then a set of planet gears, which are these 4 gears operating right here. All of the planet gears are actually in a carrier, sometimes called the planet carrier, and then you have a sun gear. And all of this would be compressed together, and they can all spin independently of each other, and they're controlled by this equation here. And the way a standard automatic transmission works is the powertrain engineer will fix one of these gears stationary, and as a result they'll put the power input through another set of gears, and they'll get the power output through the other gear, and they'll get a specific ratio. You can do a lot of different ratios depending on the form factor of the gear set, which is just the ratio of the number of the teeth on the sun gear versus the number of teeth on each individual planet. And the number of teeth on the sun gear plus 2 times the number of teeth on the planet gear always has to equal the number of teeth on the ring gear, or else it won't physically fit together. So if I hold the ring gear stationary and I run the engine power through the sun gear and I do the output power to the final drive ratio out the planet carrier, I would get a calculation of this, and this is the number of teeth on the ring gear versus the number of teeth on the sun gear. So basically one planetary gear set will give you 3 different ratios, and one of them is a reverse gear. And you can actually do more gears than that, but typically the automatic transmissions that are used today, if you want more than 2 forward gears, what they'll do is they'll stack several sets of planetary gear sets together, lock up whichever ones they want to get the desired output ratio. So you can get 2-speed, 3-speed, 4-speed, 5-speed, and now they're even getting into 6-speed transmissions, just depending on how many planetary gear sets you put in the transmission. So, with a finite gear set for transmission operation, when you come up to a stoplight, you're going to sit and idle right about there. You idle about 700 RPM, 600 RPM. You're not producing any torque, so actually you're down here. You're not producing any torque, but you are consuming fuel. Now if you take off from a stop sign at a modest amount of power, what happens is the vehicle will ramp up, the engine will start accelerating, it'll shift into second gear, it'll continue accelerating, it'll shift into third gear, it'll continue accelerating, and then it'll shift into fourth gear. Now, once you get up to the speed that you desire on the highway, then what happens is the engine will drop down in torque, and it'll lock up at whatever torque is required to overcome the air resistance and the rolling resistance. So now if you're operating on the highway and you want to pass a semi-truck or something and you step on the throttle, the transmission will downshift, the engine will accelerate, it'll go along the maximum horsepower until it reaches its maximum RPM, it'll shift, it'll go continue accelerating, and then it'll shift, and then once you pass the semi and you resume with traffic, the power will drop again, and then if your speed decelerates back to what you were doing before you pass the semi, it'll shift over to here. So you can see the engine spends a significant amount of time not in the peak efficiency spot. What if we didn't fix one gear set and instead we controlled the speed of each gear ratio independent of each other? Again, the gears are mechanically connected by this ratio, but if we, instead of using a clutch band and some type of friction pack to stop a gear set, we'll use an electric actuator to control the speed, and then we'd have dynamic gear speed control. So what you come up with is you have the engine input here, you have an electric motor connected to the ring gear, and then you have the planet carrier going out to the final drive ratio, and you can actually put an electric motor on there. The engine applies torque through the sun gear, the electric motor applies torque to the ring gear, and then you have a second motor that can apply torque to the final drive. As the engine spins and you start applying a load, you draw power from this electric motor, and you either send it to the battery pack, otherwise you can send it to this motor and it'll actually transmit power to the final drive and help the vehicle accelerate. So now you can have a smaller engine, but because you combine the horsepower of this engine with the horsepower of this engine, you have the same net power, and you can actually accelerate at the same capability of the larger engine. And this is good because now you can keep your engine at one constant speed and hopefully a constant load, and then the electric motors are efficient across a wide range of speeds, and they actually you can actually end up transmitting more power.
What type of electric motors they consider?
You can use three-phase, you can use brushless DC. It depends on what you want to use for your controller, because generally the controller for the motor is the most expensive part. And it also depends on the voltage that you want to run. Typical electric vehicles are between 200 and 600 volts, or if you wanted to use a fuel cell or a supercapacitor, it's really up to the engineer. So now what we had before, the engine, because we used finite gear ratios, the engine had to the engine speed was dependent on the vehicle speed and whatever gear you were in. Now what we can do is we can maintain a constant engine speed and then just apply various loads. And if we have a good program, we can actually keep the torque in the most efficient spot. Like I said, lower number, better efficiency. Peak efficiency occurs around 2,500 RPM. Ideally, the engine would run at 2,500 RPM continuously. For this particular motor, not all engines are the same. Some have different sweet spots. Like I said, it depended on the subsystem. But now the load can be controlled by the electric motors and the vehicle inertia as opposed to just